Hi, Assalamualaikum and a very good morning. So today we're going to do past year question for the year of 2018-2019, focusing on the matriculation program for the chemistry subject for the code of SK025. So before we go straight into the question, let us look into what is provided in the question booklet. So as far as you know that, for the chemistry subject, there going to be no formula will be given during the exam. But what is given to you is that you're going to be given the table of the relative atomic masses, where you're going to have the list of elements and their respective symbols. So you are be provided with the atomic number as well as the relative atomic masses, which indicating the molar mass. Also, you're going to be given with the list of constant in order to help you to solve problem related to the physical chemistry. So I will highlight some of the important constant that you're going to be used quite often. So one of the constant that you're going to be used oftenly in physical chemistry is the specific heat of water, which has the units or the indication of the small letter C with W here. So C, the small letter C is representing specific heat and W is representing the water. So you're going to use the value of 4.18 joule per gram per degree Celsius. And this is going to be used quite oftenly in chapter 2, which is thermochemistry. And particularly, this value will be used in order to solve problem related to the calorimeter. Next, you also be using the R value, which is the molar of gases constant R. So this value will be used quite oftenly in chapter 1, which involve the reaction kinetic. Particularly, this R value will be used in order to solve problem related to the Arrhenius equation. So the R value here will have the unit of 8.314 joule per Kelvin per mole. And the next important constant is the Faraday's. So 1 Faraday is equal to 96,500 coulomb. So you're going to use it quite oftenly in chapter 3, which is related to the electrochemistry, particularly used in order to solve problem related to the electrolysis or the electrolytic cell. Okay, so here are the list of constant and the table of relative atomic masses in order to help us to solve problem during the exam. So without any further ado, let us go straight into the question. So for question number 1, on heating the dinitrogen pentoxide, N2O5 decomposes as follows. So 2 mole of the N2O5 gases will decompose in order to produce 4 mole of NO2 gas as well as the oxygen gas. And this reaction is the first order with respect to the N2O5. So for question A1, we need to determine the rate of the formation of oxygen if the rate of the disappearance of N2O5 is 1.25 times 10 to the power of negative 2 molar per minute. So in order to solve this question, what we're going to do is we're going to do the differential rate equation. So in order to do the differential rate equation, we're going to start with rate, and we're going to use the we're going to look into the reactant here. So negative 1 over 2. So 2 is representing the stoichiometry. And then for your reactant is you have DN2O5, and it is divided by time, the differential of time. And then the negative sign here representing a reactant, where reactant will be reduces over time because some of the reactant will be converted into product. And we're going to compare that with our product. So as time increases, our product will be increases. So positive 1 over, so the stoichiometry here is 4, and then our product here is DNO 2 over dt. And then we can also compare that again with the oxygen. So here we're going to have 1 over 1. So we can just put it as dO2 over dt. So 1 over 1 is still 1, and then the positive sign here representing a product is being formed. Okay, and in order for us to solve question number 1, we're going to compare the rate of the formation, so dO to dt, with the rate of the disappearance of N2O5. So here is the disappearance. So we're going to compare these two boxes here. So let us do that. So we're going to get our rate is equal to the dO dt, which is the rate of the formation of oxygen. And then the rate of the disappearance is equal to the negative 1 over 2 dN2O5 over dt, where negative here representing the reactant and 2 here representing the stoichiometry. Okay, so the rate of the disappearance is given as 1.25. So the disappearance here is meaning by the negative sign. So you know that the d over dt, which is N2O5, is equal to 1.25 times 10 to the power of negative 2 molar per minute. Okay, so the negative here representing a disappearance. Dia dah kehilangan lah. Alright, so we can put it, the negative to be together, and then 1 over 2 is going to be plucked out of the bracket. And then this value here is we know the value to be 1.25 times 10 to the power of negative 2. So we're going to substitute that in. And then as a result, we can just do some multiplication and do some maths here. And lastly, we're going to get the rate of the formation, which is positive, means dihasilkan, is equal to 6.25 times 10 to the power of negative 3 molar per minute. Okay, so that's all for question A1. For question A2, we need to calculate the rate constant for this reaction if 25% of N2O5 is decomposed within the 10 minutes. So from here, we need to find the rate constant. So our rate constant here is the K. Okay, and we know that this reaction is a first order reaction because it is given in the question here. So since we know that it is a first order reaction, we know that we need to use the integrated rate equation to be ln N2O5, which is our concentration of the reactant, equal to the ln N2O5 original or the initial minus KT. Okay, so this is the formula that you need to use. And then initially, you know that our initial concentration of our reactant is 100%, which is N2O5 initial to be 100%. But after 10 minutes, 25% is reduced, is decomposed. Okay, we lost 25%. So after 10 minutes, what we're going to left is 75%. So this is our concentration of N2O5 at time t, where t here is 10 minutes. So 25% has been decomposed. So we're going to substitute our 75 here and then our N2O5 to be 100. Okay, and then K is something that we need to find out, and then T here is in 10 minutes. Okay, so we're going to solve the maths here, and then we're going to get our K to be 0.0287 per minute because our time here is in minutes. Okay, be careful, it is not per second, yeah, it is in minutes because we are using minutes. Okay, and then we need to determine the half-life for this decomposition reaction. So since you know that it is a first order reaction, so you need to use the half-life for the first order. So the half-life for the first order reaction is P half is equal to the ln 2 over K. So K here is already determined in A2. So we just substitute that in, ln 2 divided by 0.0287. So once we do the maths, we're going to get the half-life is 24.15 minutes. Okay, so that's all for question A3. Now for question 1b, table 1 shows the rate constant for the decomposition of N2O5 at two different temperatures. So at the temperature of 25 degrees Celsius, the rate constant is 1.74 times 10 to the power of negative 5 per second. And at the temperature of 35 degrees Celsius, the rate constant going to be 6.61 times 10 to the power of negative 5 per second. So for question B1, we need to determine the activation energy, EA, for this reaction in kilojoule per mole. So when it involves two different temperatures and two different rate constant, what we're going to do is we're going to use the Arrhenius equation, which involves two different temperatures. So we're going to use the formula of ln K1 over K2 equal to EA over R 1 over T2 minus 1 over T1. Remember, the top is K1 and we must end it with T1 here. So in order to use the Arrhenius equation, our temperature here need to be in the unit of Kelvin. So the temperature, which is in degrees Celsius, need to be converted into Kelvin by adding up with 273.15. So at the 25 degrees Celsius or at the 298.15 Kelvin, our K1, our rate constant one, is 1.74 times 10 to the power negative 5. Or at the temperature of 308.15, which is adding up 35 with 273.15, we're going to get the K2 to be 6.61 times 10 to the power negative 5 per second. Okay, so there are two important statements here. Okay, and once we got this information, we're going to substitute this value into this equation. So ensure that you substitute that correctly. So let's say our K1 here, which is denoted in the yellow highlighter. So K1 substitute here and T1 substitute there. Okay, and so carefully, K1 1.74 times 10 to the power negative 5 per second, and then our T1 is 298.15. Similarly for T2, so let's say our K2 here 6.61, so here, and then our T2 308.15. Okay, so ensure that you substitute it correctly. Okay, and for our R value here, R is referring to the universal gas constant, or you can see that in the list of constant at the beginning of the video that I have just shown. So this referring to the molar gases constant, where it's going to have the value of 8.314 joule per mole per Kelvin. So we can settle this part first. So 10 times 10 to the power negative 5 times 10 to the power negative 5 per second, and per second can be cancelled out. So when we settle the left hand side, we're going to get the value of negative 1.3347. And then if we were to settle on the bracket on the right hand side, we're going to get negative 1.088 times 10 to the power negative 4 Kelvin. So Kelvin and per Kelvin can be cancelled out. Okay, so we can multiply that and then divide that with negative 1.088 times 10 to the power negative 4 here. So once we do the maths, we're going to get our EA to be 0.01950 joule per mole. Okay, but the question asks us to write it in terms of kilojoule per mole. So we need to divide that with 1000. So lastly, what we're going to get is EA to be 0.01.95 kilojoule per mole. So this is how you do question B1. For question B2, it stated that activation energy can also be determined graphically. So we need to sketch the graph and explain briefly. So sketch here means it does not drawn to scale. Okay, dia hanyalah lakaran sahaja. Okay. So in order to get the activation energy, as usual, we need to look at the Arrhenius equation. So our original Arrhenius equation is K is equal to AAE negative EA over RT. And we can ln both sides. So we're going to get ln K is equal to ln A, or we can put negative EA over RT plus ln A. Okay, so this is what you're going to get. And then you can make it nicer by putting it like this. 1 over T plus ln A. So you can use this equation in order to compare that with y is equal to mx plus c. So your y-axis is going to be ln K, your m going to be negative EA over R, your x going to be 1 over T, and then your c is the ln A, which is your y-intercept. Okay, so by using this idea, you can sketch the graph. Okay, so let us put it nicely in words. So you know that you're going to put it as ln K equal to EA over R times 1 over T plus ln A, which I have written it here. And then, as I mentioned, you need to compare that with Y is equal to mx plus C. Your M here is this one, and then X is your this value, and then C is ln A. And then from here, you're going to sketch the graph Y, which is ln K, and your x-axis is going to be 1 over T, and then your M is equal to negative EA over R. Okay? So you're going to get the value to be, the graph to be like this. And you know that your gradient or your slope going to equal to M. So therefore, you know that M is equal to the negative EA over R. So we can determine the activation energy EA by multiplying our M with our R value here. So EA is equal to the negative M multiplied by R. And hence, we can put that in words. We can say that the activation energy can be obtained from the graph shown by multiplying the slope of the graph with the universal gas constant R. And from here, the activation energy can be determined by using the graph that we have sketched. Okay, so that's all for question 1b. Now for question number 2, in an experiment to measure the enthalpy change of neutralization, 25 ml of 1.0 molar HCl is placed inside a polystyrene cup. At the same temperature, 25 ml of 0.1 molar NaOH is added and stirred. The temperature of the resulting solution increases by 7 degrees Celsius, and hence we need to calculate the enthalpy of the neutralization for this reaction. And it was stated that the density and the specific heat capacity of the final solution are the same as the water. So in order for us to visualize this reaction better, let us look into the diagram below here. So we have a polystyrene cup and then we have a thermometer. So initially we have 25 ml of 1.0 molar HCl inside the polystyrene cup. And we're going to add another 25 ml of 1.0 molar HCNaOH into this polystyrene cup. And then this polystyrene cup will be closed using a rubber, and then in order to prevent the heat loss to the surrounding. And then we're going to put a stirrer in order to mix the reaction. So from here, we know that there is a reaction between HCl, which is an acid, as well as the NaOH, which is a base. And from here, we can calculate the heat of the reaction using the formula of Q reaction, MS CS delta T, where the solution is equal to water, where MW CW delta T, because it was stated here it is the same as water. So initially, they have 25 ml of HCl, but now we add another 25 ml of NaOH. So therefore, our final solution will be 25 plus 25 ml, so we have 50 ml. So it has the same density as water, so 1 gram per ml. So if we have 50 ml, so we're going to get 50 gram of the water being produced. So we're going to put the formula for the Q reaction is equal to MSCS delta T, where you know that the solution is equal to the water. Okay, and then we're going to substitute the mass of the solution or the mass of the water, which is 50 gram because we add up two of them together. And then our specific heat capacity of the solution or the water is given in the list of constant, okay, at the front page of the booklet. So we're going to have 4.18 joule per gram per degree Celsius. And then our delta T here is known to be 7 degrees Celsius because when there is a mixing of HCl and NaOH, the temperature rises up as much as 7 degrees Celsius. So here is the delta T. Okay, so we're going to plug in here, and then degree Celsius and per degree Celsius, gram and per gram can be cancelled out. And lastly, we're going to get the unit of joule. So once we do the maths here, we're going to get the heat to be 1463 joule. Okay, and now we can make an equation because, as I mentioned before, it is a neutralization reaction between an acid as well as a base. So HCl and NaOH aqueous reacted in order to produce NaCl aqueous with water. So from here, we can find the number of mole of the water from the comparison of the base as well as the acid. So we know that mole of HCl is equal to the mole of NaOH, and it is also equal to the mole of water because the ratio is 1 to 1 and then to 1. And from here, HCl and NaOH have the same volume, which is 25 ml for NaOH. HCl is also 25 ml. The molarity is also similar, 1.0 molar, and then the molarity here is 1.0 molar. So that is why the molarity is the same. So the same number of mole of water going to be produced. So this comparison here, according to water, is compulsory to be written in order to get the mark. Because for the heat of neutralization, it is basically defined as the heat release when 1 mole of water is formed from the neutralization between acid and base. So that is why you always need to compare with the mole of water. So from here, you can find the mole of the water by using mv divided by 1000, where the volume here is in ml. So our molarity is 1.0 molar, and then our volume is 25 ml divided by 1000. So our number of mole here is 0.025 mole. Okay, so in order to find the enthalpy of neutralization, we can use the formula of delta H is equal to Q over N. So we're going to put delta H is equal to Q reaction divided by N, where our heat of the reaction is 1463 divided by our number of mole of water, which is 0.025 mole. And then from here, we can get delta H to be 58,592 joule per mole. And from here, we can convert that into kilojoule by divided by 1000. And then you know that the definition of the heat of neutralization is the heat release. Okay, so when we mention about heat release, we're going to have a negative charge. So negative sign. So we're going to put a negative sign here, where the negative sign indicates that heat is being released due to the neutralization between an acid as well as a base. Okay, and similarly, you can also do a comparison. If you want to do another method, you can also try 0.025 mole of H2O will produce 1463 joule. So let's say if you have 1 mole of H2O, how many joule will you get? So you can do a cross multiplication, and then you will also get similar answer, which is 58.52 kilojoule per mole here. Okay, so you can use this method, or you can also use the comparison method in order to get to your answer. All right, now we're going to look into question 2b. So for question 2b, the thermochemical data for the formation of the sodium oxide Na2O is given in the table 2 here. So based on the table number 2, we need to construct a Born-Haber cycle for the sodium oxide, and we need to calculate the enthalpy of atomization of the sodium. Okay, so we need to do these two things. So at first, let us start by doing the each equation for each of the enthalpies. So as what we have learned, in order to construct a Born-Haber cycle, the easiest way is to follow the acronyms of F, A, I, E, L, FAL. So you start with the formation first. So enthalpy of formation, which is the sodium oxide. So we need to produce 1 mole of the sodium oxide, Na2O, which is in solid. And hence, we know that it need to comes from its neutral stable element, which is Na solid, plus oxygen, which is in the gaseous state. Okay, and from here, in order to get to 1 mole here, we need to put 2 Na and then 1/2 oxygen. Okay, so we have done the formation equation here. Next, we need to do the atomization. So for atomization of sodium, it is not given in the enthalpy list here. Okay, so but logically it should be Na solid become Na gas. Okay, so that's atomization of for Na. Now we need to do atomization for oxygen. So atomization of oxygen is here. So O2 gas, which is 1 over 2 here, will produce O gas here. So it's going to become 1 mole of gaseous atom. Okay, from molecule become an atom. And then we have done atomization of oxygen. Now we need to do the ionization energy for the Na, which is our metal. Okay, so ionization energy is for the metal. So ionization energy is Na. So ionization energy means it need to remove 1 mole of electron from its gaseous atom. Okay, so from Na gaseous atom, it's going to become Na gaseous ion plus 1 mole of electron. Alright, so ionization energy for Na is done. Okay, because ionization energy is for metal. Electron affinity is for non-metal. So our non-metal is oxygen. So oxygen gas will receive 1 electron, will become O minus gaseous ion. Okay, so first electron affinity we have did. Now we need to do the second electron affinity. So O minus gaseous plus another electron will become O2 minus gaseous ion. Okay, so we have done with that. Now we need to do the lattice energy of the sodium oxide. So lattice energy of sodium oxide is basically the combination of the Na plus gaseous ion with O2 minus gaseous ion in order to form ionic solid Na2O solid. Okay, and then here it need to have 2 mole here. Okay, so here is the lattice energy. Alright, so these are the equation that we need to do step by step before we convert that into a Born-Haber cycle. So for drawing of the Born-Haber cycle, there are 2 methods. So let us look into method number 1 first. So for method number 1, you can use the energy level diagram where you draw the axis, y-axis with an enthalpy value, and then as usual start with the formation first. So our formation, which is here, you just write back your 2Na solid plus half oxygen gas will produce Na2O solid. So because it is negative in value, so you're going to go down. So in order to produce your Na2O solid. Okay, so we have done our enthalpy of formation for the Na2O solid. And this is going to give the value of negative 414. So you're going to put down the value of negative 414 kilojoule. Okay, next you're going to do the atomization. So atomization of Na. So you're going to look into the atomization of Na, which is below here. Okay, so atomization of Na. So 2Na will produce 2Na gas plus half oxygen gas. So what changes here is solid become gas. Solid become gas. When you have 2 mole here, it's going to become 2 mole here. Okay, and that is why I'm going to put it as 2 times the enthalpy of atomization of Na equal to X joule. Because the value here is not given, and then we need to figure out in step number 2 here. Okay, so we have done for A and A. Now we're going to do the atomization for oxygen. Atomization of oxygen is given as here. So half oxygen gas molecule become oxygen gas. So we're going to draw a line from half oxygen gas become oxygen gas molecule become oxygen gases atom. So it's going to give the value of 249 kilojoule. The others you just copy back. because the change what changing here is the oxygen. Okay, so we have done this one, and then now we're going to look into the ionization energy. So ionization energy is for sodium. So from Na become Na plus electron. Okay, but now we have 2Na. So basically it's going to become 2Na, 2Na plus, and then 2 electron. So this value here will be multiplied by 2. Okay, so we're going to make a line. So 2Na gas plus 2 electron plus oxygen. So what changes here is this part. Okay, and then 496 multiplied by 2, you're going to draw the value here, which is 2 times 496, it will become 992 kilojoule. So because it is larger in value, so it will have a larger gap. Okay, lagi besar lah dia punya arrow tersebut, jarak antara arrow. Okay, now we have done with the ionization energy of Na. Now we're going to focus on the electron affinity of the oxygen. So electron affinity of oxygen, we do the first electron affinity first. So from O, it will take 1 electron first to become O minus. So oxygen here will take 1 electron. So it will go down by negative 141 kilojoule. So it will go down, and then 2Na gas, we just copy back. And then 1 electron is being transferred into oxygen to become O minus gases. And then it's gonna go down by negative 141. So we're gonna put it here. And then for the second electron affinity, it will increase in the enthalpy, which is plus 750. And then this 1 electron here will be transferred to O minus in order to become O2 minus gaseous. Okay, so we're gonna increase by 750, and then our O minus here will become O2 minus with a value of 750. Okay, so we have done this one as well. And lastly, we're going to do the lattice energy. So lattice energy is from the 2Na plus gaseous ion and reacting with O2 minus gaseous ion in order to form Na2O solid. So we're going to make a line, go down there, which is this part, and then it's going to give the value of negative 2478 kilojoule. Okay, and similar goes to our ionization energy here. So if you were to look back, 2Na gas become 2Na plus gaseous, right? So don't forget the positive sign here, and then also the positive sign here, and then positive sign here. Okay, all right, so this is the method number 1 in order to make the Born-Haber cycle. Okay, and from your understanding here, you can also do the method number 2 in the next page here. So here is the method number 2, where in my opinion, the method number 2 is a much easier way in order to solve question B1 and B2 in comparison to method number 1. And similarly, we can use the acronym of FAIEL, which is FAIEL method. So we're going to start with the enthalpy of formation first in order to construct the Born-Haber cycle. So for the enthalpy of formation, we're going to have the Na solid reacting with half oxygen gas in order to produce Na2O solid. So we have the value for the enthalpy of the formation going to be negative 414. Okay, and now we're going to look into the enthalpy of atomization for Na. So enthalpy of atomization of Na, we don't have the value because we need to find out this value here in step number 2 here. Okay, so for the enthalpy of atomization of Na, so it can be Na solid, it's going to be converted into Na gas. So since it involves 2 mole of Na solid to 2 mole of Na gas, so our enthalpy of atomization going to be 2 times HANA, which having an unknown X kilojoule. Okay, so enthalpy of atomization of Na is done. Now we're going to do the enthalpy of atomization of oxygen. So we have half oxygen gas. It's going to be converted to 1 mole of oxygen gaseous atom. So this value going to be positive 249 kilojoule, which is here. Okay, and once we're done with the enthalpy of atomization, we're going to look into the ionization energy. So for the metal, which is the Na. So ionization energy for the sodium, we have Na, it's going to become 2Na plus. Okay, so it's going to produces 2 mole of electron as the byproduct here. Okay, and since it involves 2 mole, so the value here need to be multiplied by 2. So it's going to be ionization energy of Na, 2 times 496 is going to become 992 kilojoule. Okay, so we're done with ionization energy for Na. Now we're going to look into the electron affinity of Na. Okay, so electron affinity is for non-metal, which is the oxygen. So oxygen will have 2 electron affinity. So it will receive electron one by one, where oxygen will attract 1 electron, which is the first electron affinity. So it's going to become O plus 1 electron will become O minus. Okay, so it's going to have the value of negative 141. Okay, and then the second electron, so 1 electron has been used up, and then another electron will be attracted to the O minus, and then we're going to have the second electron affinity, which has the value of 750. So negative 141 is done, positive 750 is done. Okay, so now we have the lattice energy of the sodium oxide. So lattice energy of sodium oxide is 2Na plus gaseous plus O2 minus gaseous ion in order to produce ionic solid Na2O solid, which is negative 2478. Okay, and from here you can find out the value of the HANA from your Hester's law. So A going to D is equal to the addition of this thing plus this thing plus this thing plus this thing and plus this thing. So from here you're going to have delta HF is equal to the addition of 2 HANA plus HAO plus IENA plus first ionization energy of oxygen plus second ionization energy of oxygen and then plus delta H lattice. Okay, so we're going to plug in the value here. Delta HF is equal to negative 414. HANA we need to find out. HAO is 249. Ionization energy is 992. First electron affinity of oxygen is negative 141, so don't forget the negative here. Second electron affinity is 750, and then lattice energy is negative 2478. So once we do the math, we're going to get our 2HANA to be 214 kilojoule. And if we were to find the enthalpy of atomization, which is HA, so 214 divided by 2, we're going to get the HANA, which is enthalpy of atomization for sodium, to be positive 107 kilojoule per mole. So the per mole here refer to 1 mole of Na, and that is why we got per mole at the end of the answer here. Alright, so this is how we do question number 2B. Now we're going to look into the next question, which is question number 3. So for question 3A, a galvanic cell is constructed based on the notation below. So we have our zinc solid, become zinc 2 plus aqueous ion. They're going to be a bridge, and then they're going to be a reduction process of Ag plus aqueous in order to form Ag solid. So here is the cell notation. So you have at anode, here is bridge, and then here is at the cathode. So here is the oxidation process, and here is the reduction process at cathode, and the double line here referring to the salt bridge. So it was mentioned that the cell potential is 1.58 volt. So cell potential is the E cell, 1.58, when the concentration of the zinc 2 plus and Ag plus are X molar and 0.15 molar respectively. So calculate the value of X. So our zinc 2 plus concentration have an unknown X. Meanwhile, our Ag plus will have the concentration of 0.15 molar. Okay, and it was given the standard cell potential to be positive 1.56 volt. So from here, we can make the Nernst equation in order for us to figure out the concentration of X. So here is our Nernst equation where the cell potential is equal to the E naught cell minus 0.0592 over N log Q. And in order to find the log Q or the reaction quotient of Q, we need to do the overall cell reaction by doing the reaction at anode as well as the reaction at cathode. So for the reaction at anode, we know that our zinc will undergo oxidation to form zinc 2 plus and produces 2 electrons. Meanwhile at cathode, we have our Ag plus becoming Ag solid. And then we need to multiply all the equation by 2 because the 2 electron here and 2 electron here will need to be cancelled out. And as a result, we're going to get the overall equation to be zinc solid plus 2Ag plus aqueous ion, arrow, zinc 2 plus aqueous plus 2Ag solid. So here is the overall cell reaction. And from here, we know that the electron transfer involved for the overall cell is N is equal to 2, where N equal to 2 is the number of electrons, so we can plug in here. And then our log Q is depending on the overall cell reaction, where our Q is basically the concentration of the product, which is zinc 2 plus, divided by the concentration of the reactant, which is our Ag plus, and then the stoichiometry to the power of 2. For the solid, and solid here, we can ignore that in the reaction quotient. So untuk solid, kita akan abaikan dalam reaction quotient. Kita hanya melibatkan aqueous ion or the gaseous ion. Okay, so we're going to put it nicely here. So E cell is equal to E naught cell minus 0.0592 over our N here is 2, so we can substitute. And then our log, zinc 2 plus, bracket, Ag plus to the power of 2. Okay, so jangan tinggal nombor 2 di sini. Okay, so our E cell, we know the value is 1.58, so we can substitute. Our E naught cell, which is standard cell potential, is given to be 1.56. And then our log, zinc 2 plus will have the concentration of X, and then Ag plus will have the concentration of 0.15. Substitute that in here. So we're gonna make some calculation by using calculator. So bring it to the left hand side and then divide that with that value. And then we're going to get this value here, which is negative 0.6757. So double check your answer. And then we're going to anti-log. So we're going to get x divided by 0.15 square is equal to 0.211. And then from here, 0.15 square, we're going to bring it to the right hand side. And then we're going to get the value of x. And therefore, the value of x here to be 4.75 times 10 to the power of negative 3 molar, where the value of x here is referred to the concentration of the zinc 2 plus. Alright. Now we're going to look into question 3b. So for question 3b, a charge of 0.025 Faraday, so our charge is Q here, was passed through an aqueous solution of Mn plus. So aqueous solution means that they're going to be water inside the reaction, and then they're going to have Mn plus aqueous ion using a current of 2 ampere. So we have our I. So an amount of 0.79 gram of M was deposited at the cathode. So given the molar mass of M is 63.2 gram per mole. So our I here is 2 ampere. And then we need to calculate the time taken in minutes for the deposition of M. So we know that our charge here Q is equal to 0.025 Faraday. And 1 Faraday is equal to 96,500 Coulomb. So we can find our Q in terms of Coulomb to be 2,412.5 Coulomb. So now we can use the reaction or the formula of Q is equal to IT. So our Q here is 2,412.5 Coulomb, and then our I here is the ampere, and then we got the time. So By using simple maths, we can now get the time to be 1206.25 seconds. So remember that the time here is always in the unit of second. Okay, now for question B2, we need to calculate the volume of oxygen gas liberated at anode at standard temperature and pressure. So in order to find the volume of oxygen gas, we need to do the equation at anode. Okay, so we know that in an aqueous solution, they're gonna be water, right? So water gonna be oxidized at anode. So at anode, water gonna be oxidized, where 2H2O liquid will produces oxygen gas plus 4H plus aqueous ion plus 4 mole of electron. So double check, make sure the number of electron is correct, and then the stoichiometry is also correct. So from here, I know that this is correct, and from here I can make a comparison where 1 mole of oxygen will produce 4 mole of electron, and 4 mole of electron is equal to 4 Faraday. Okay, but from the equation, I only know I have 0.025 Faraday. So what I can say that 0.025 mole of Faraday is equal to 0.025 mole of electron, and I can find the number of mole of oxygen that I have. Okay, so from here I can do a cross multiplication. So if I were to do cross multiplication, I'm gonna get 4x is equal to 0.025, and then from here I can find the value of x, where x here is equal to 6.25 times 10 to the power of -3 mole of O2. So here is the number of mole of oxygen liberated at anode, and from here I can use the molar volume, which is at standard temperature and pressure. The molar volume is 22.4 dm cube. If at room temperature and pressure, it's gonna be 24 dm cube. So be very careful because the question asks about STP. Okay, so you're gonna use this volume here. So in order to find the volume of oxygen, is basically equal to mole multiplied by the molar volume of oxygen, where 6.25 times 10 to the power of -3 multiplied by 22.4 dm cube, and hence we're going to get the volume of oxygen to be 0.14 dm cube. Okay, so this is how you solve question 3b1 and 3b2. Now we're going to look into question number 4. So for question number 4, compound A is a fourth-membered ring alkane with a molecular formula of C5H10. So for question 4a, we need to draw the structural formulae for all possible mono-substituted products for the reaction between the C5H10 and chlorine in the presence of light. So at first, we need to identify compound A first. As mentioned, it is a four-membered ring alkane. So we know that it's going to be a cycloalkane, which is 1, 2, 3, 4 cyclobutane. And then another carbon here going to be branch, which is CH3. Okay, so if you were to check C, 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 C here, you're going to have CH2, 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 and then CH here. The number of carbon that we have is C5. The hydrogen that we have is 10 altogether. So we know that our structure here is correct. So our compound A is be looking something like this. And then when it reacted with chlorine in the presence of UV, we're going to get a mono-substituted products. Okay, mono-substituted means that one of the hydrogen, doesn't matter at which position, H is being replaced by Cl. Okay, salah satu hydrogen digantikan dengan Cl. So that is what meant by mono. One hydrogen atom replaced by Cl. So at which position of hydrogen can be replaced by Cl? So there are few possibilities. So first thing, we can say that H here can be replaced by Cl. So H here can be replaced by Cl in order to become this one. So here is one mark. And then we can also say that because this one got 3 hydrogen, right? H, H, and H. So one of the hydrogen can be replaced with Cl. So it's going to become like this. So here another mark. And then another possibility is at this position because we have hydrogen here or hydrogen here, or hydrogen here or hydrogen here. So because it is symmetry, you can choose on this side or you can choose on that side. Okay, so let's see if I'm changing this side. So I'm going to Cl going to be here, or I can choose the other side here. So my Cl can be on the top side here. So either one of these will be carrying another mark. Okay, and then the last mark here is hydrogen on this side. Okay, so you can choose here or here. So if I were to change this one, I'm going to get Cl here. So it's going to have another mark here. So for question A, it will carry 4 marks. Then we're going to do question B. So write the reaction mechanism for the formation of the most stable reaction intermediate in 4A. Okay, so which one of these will be the most stable? So the answer is this one, the first one, because it is a tertiary haloalkane, and it also gonna produce a tertiary free radical, which is the most stable in order to produce tertiary haloalkane. Okay, this one is primary, secondary, secondary, and secondary haloalkane. So this one is tertiary. Okay, so we know that it is the most stable. So for here, we need to write the reaction mechanism, and as what you know, the reaction mechanism for the free radical substitution of an alkane will have 3 steps. So step 1 initiation, step 2 propagation, and step 3 termination. For the step number 1, we're going to start off with our Cl molecule, where Cl molecule in the presence of UV, it can be broken down because this bond here will have 2 electrons. So by using UV, it's going to have enough energy to undergo homolytic cleavage, where 1 electron going to be passed on the left hand side, and then another electron will be passed on the right hand side. Satu electron sini dan satu electron sana. As a result, we're going to produce Cl free radical and another Cl free radical. So half-headed arrow here means the transfer of 1 electron. Half-headed arrow, 1 electron. The next step is the propagation. So for the propagation, we're going to use our chlorine free radical in order to react with our alkane, with our cycloalkane here. So here is compound A, and then we need to focus on this hydrogen because this one going to produce the more stable free radical. Okay, because more stable reaction intermediate, right? So it is referring to the free radical. So here we're going to react with your chlorine free radical. So this consists of 2 electrons. So 1 electron from here. This consists 2 electrons. So 1 electron is used for the hydrogen to react with the chlorine free radical. And then another electron will be passed to this carbon here of the cycloalkane. So as a result, H and Cl can be formed together, and a radical gonna be formed because 1 electron is being passed here. Okay, so for question B, you're gonna have another 3 marks. So the first mark here is the equation with complete UV and the arrow. So here is 1 mark on the initiation. Second mark is going to be at this side. So you need to show a complete arrow. Another 1 mark here. And then you need to label this one as the most stable reaction intermediate, which is another mark here. So you're going to have 3 marks altogether for question 4B. The other steps below here will not carry any mark because the question asks us for the formation of the most stable reaction intermediate. So you can stop until here. Okay, so usually question will ask you about the formation of major product, but now for this question it asks you until reaction intermediate, so you can stop until here. But anyhow, I'll just continue until the end just for the sake of learning. Okay, untuk tujuan pembelajaran, I will just continue until termination step. Okay, so for this one, we have the reaction intermediate from what we have produced. and then it's gonna react with the chlorine molecule once again. So it's gonna break the bond here, one electron, and then here one electron gonna be passed there, and we're gonna produce our major product, Cl here, and then Cl radical gonna be produced once again. Okay, and as for termination step, termination means terminator, menghapuskan. Kita nak hapuskan apa? We're gonna hapuskan the radical. So it is a reaction between radical and radical. So we have chlorine radical react with another chlorine radical. So one half at the arrow reacting with half at the arrow in order to produce chlorine molecule. Or we can say that the cycloalkane radical will react with the chlorine radical in order to produce our major product once again, which is here. Or you can also say that the cycloalkane radical will react with another cycloalkane radical, like that and like that, in order to produce an alkene here. Okay, and as I mentioned, this step below here will not have any marks. The marks will be allocated at the top side here. Okay, and below here is just for the sake of learning. Okay, so that's all for question number 4. Now we're going to do question number 5. So for question number 5, compound B and C are hydrocarbon with the structural formulae as shown below. So for question 5a, we need to name the compound B and C according to the IUPAC nomenclature. So for compound B, it is an alkene, which is a cycloalkene. So we need to find the longest carbon chain. So we have 1, 2, 3, 4, 5, 6. So we know that it is a 6 carbon. So it's going to be cyclo because it's a cyclic, and then it's going to be hexene because it is an alkene, cyclohexene. And then at carbon number 1, it is attached with the methyl group. So it's going to be methyl cyclohexene. And for number 1 here is optional. So you can write 1 methyl cyclohexene or methyl cyclohexene. Okay, so for B, it's going to be methyl cyclohexene. And for C, you're going to have a benzene ring. So benzene, and then you're going to have a methyl group. So it's going to be methyl benzene, or the whole structure here will have a special name known as toluene. So for C, it's either methyl benzene or you can write it as toluene. All right. And now we're going to look into question number B. So for B, both B and C can undergo oxidation reaction with the same oxidizing agent. So we need to write the chemical equation involved and explain the differences between these two reactions. So B and C can undergo oxidation. So using the oxidizing agent. So oxidation agent that we're going to use is the KMnO4 H plus with kit. Okay, so we need to write it all down and make an equation because the question asks us to write the chemical equation. So we have B here, which is our methyl cyclohexene, reacting with the KMnO4, which is oxidizing agent, at acidic condition at high temperature. So what's going to happen here is that it's going to undergo oxidative cleavage. So it's going to break the bond here. So as a ring, it's going to break apart the ring. So in order to determine the product, we can number the carbon here in order to visualize the situation clearly. So let's say if we number the carbon number 1 here, number 2, number 3, number 4, number 5, number 6. So at first it's going to be a ring, but now we cut the ring. So what's going to happen here is that we're going to get a aliphatic carbon chain. Okay, seolah-olah macam cincin ataupun getah gelang. Bila diputuskan getah gelang tersebut, bila dipotong, dia akan dapat memanjang. So we're supposed to get a straight chain alkane. So from here, we know that we need to have 6 carbon, where the other carbon here is attached to the carbon number 1. So we're going to draw 1, 2, 3, 4, 5, and 6. 5 and 6 here. So at carbon number 1, it is attached with CH3. Okay, and then at carbon number 1, the double bond here will be oxidized to become oxygen because it already been cleaved. Okay, And then we need to do the numbering. Okay, sorry. So here gonna be, we know that you're gonna have 6 carbon, and now this carbon number 1 will be attached with carbon number 6 because number 2 has already been cut off. So number 2 will be at the end here. So it's gonna be 1, 6, 5, 4, 3, and 2. Okay, so 6, 5, 4, 3, 6, 5, 4, 3, and the number 2 here will be at the end, in which the double bond O, the double bond region here will become double bond O, and then going to become OH here. So if we were to connect them again, it's going to become a cyclic. Okay, so that is why it is important to number so that we can see the situation clearly. Okay, so we're going to get the answer to be like this. So 1, 6, 5, 4, 3, and 2. So if we were to connect number 2 and number 1 again at this region, what we're going to get is a cyclic again if we were to reverse the reaction lah. Okay, but then if from cyclic, we're going to get the aliphatic here. And as for the reason here, you can say that the oxidative cleavage or the breaking of carbon-carbon double bond occurs for the cycloalkane B. Meanwhile, for C, which is the toluene, where it undergo oxidation using the same oxidizing agent, which is KMnO4, H plus with heat, what we're going to get is the formation of the carboxylic acid, which is the benzoic acid. So the CH3 here will be converted into COOH. So it doesn't matter how long is the carbon chain, as long as there is a benzylic hydrogen, it will be converted into benzoic acid. So side change oxidation, which is happening at the site, occurs for alkyl benzene C as there is a presence of the benzylic hydrogen. So this one can be converted into benzoic acid. Now we need to focus on the next question, which is C. Name one reaction that converts B, which is methyl cyclohexene, into methyl cyclohexane. Okay, so this one is cyclohexene, become methyl cyclohexane. So from alkene become an alkane. So from here, you can undergo the process of hydrogenation, or we can say that a catalytic hydrogenation. For example, H2 using platinum or palladium or nickel. So it will undergo the process of hydrogenation, and catalytic here refers to the catalyst. Or you can say that it can undergo the process of reduction because it accepting the hydrogen in order to form alkene. So both of these answer will be accepted. Okay, that's all for question number 5. So now we're going to look into question number 6. For question number 6, it was stated that two organic compound D and F with the molecular formula of C4H9Br react with suitable reagent to form E and G via SN1 and SN2 reaction respectively. Both E and G have a molecular formula of C4H10O. So for question 6a, we need to draw the structural formulae for D, E, F, and G. And in order to understand this question better, as usual, we need to start off with an idea. So when we read the question again, we know that the organic compound D and F will have the molecular formula of C4H9Br and C4H9Br also for F. And then the D here will react with suitable reagent in order to form E via SN1 reaction. Meanwhile, for F, it also going to react with suitable reagent in order to produce G via SN2 reaction. Okay, both E and G here will have the molecular formula of C4H10O. Alright, so here are the ideas. And from here, when you know that reaction D uses SN1, you will know that it will involve 2 steps, and it usually happens for a tertiary haloalkane. Okay, so you have learned this in your lecture and it's supposed to come to you naturally. So as I mentioned, SN1 will involve two steps and usually happens for the tertiary haloalkane. And since it involves SN1 reaction, it usually involves weak nucleophile as for our reagent. Okay, so reagent kita mesti menggunakan weak nucleophile. Meanwhile, for SN2, it will involve one step and it usually occurs for a primary haloalkane. Okay, so SN2, one step and primary haloalkane, and our reagent here need to come from the strong nucleophile. Okay, so here are the idea. Okay, so from this understanding, we need to figure out D, E, F, and G. So our haloalkane here will need to be tertiary haloalkane. So we know that we have four carbon. So 1, 2, 3, and 4. So CH3, 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 and then Br. So from here we have four carbon and it's going to become tertiary haloalkane. So the most suitable one going to become this answer here. Okay, or you can also use skeleton structure to become Br here. Okay, meanwhile for F, it need to be a primary haloalkane. So it's going to be 1, 2, 3, and 4, and it's going to become Br at the end here. Okay, or you can also written that to be CH3, CH2, 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 Br. Okay, and for the product here, the Br, this one is D. For E, the Br here will be changed with OH. Okay, from C4H and Br, you will add another H to become H10, and then O will be adding to become O here. So Br will be replaced with OH. So you know that it's going to become a tertiary alcohol. So in order to get to the tertiary alcohol, we need to use our weak nucleophile. And the most relevant answer for the weak nucleophile is water, because it has the OH group and then it is having a lone pair which is weak. Meanwhile for G, we started off with like this and then it's going to become like this. So Br going to be replaced with OH and then we need to use a strong nucleophile. Let's say NaOH because it have a negative charge here, and for this situation reflux is needed. Okay, so in order to determine, let us write it down nicely. So for the structural formula of D, we know that it's going to be a tertiary haloalkane, so it's going to be something like this. And for E, it's going to become tertiary alcohol because Br going to be replaced with OH. For F, it's going to be a primary haloalkane, which has 1, 2, 3, 4 carbon, and then it's going to be Br here. And for G, Br going to be replaced with OH. Okay, and for question B, we need to suggest a reagent for the formation of E and G. And as mentioned, E here need to be a weak nucleophile. So our E are going to be H2O with the condition of reflux. Meanwhile, for the reagent for the formation of F, we need to use NaOH because it is a strong nucleophile. OH minus, it has a negative charge, so it is a strong nucleophile. And then the condition here need to have the reflux. Okay, so this is by using the idea here, we can answer A and B respectively. Now for question number C, we need to write the mechanism for the formation of E. So you know that for the formation of E, it involves two steps. So step number 1 is the formation of the carboxylic ion, and for step number 2 is the nucleophilic attack on the carboxylic ion. So we started off we will start off with drawing our D here, which is our tertiary haloalkane. So this tertiary haloalkane will be broken down to be like this in order to form a tertiary carboxylic ion, where this one is a slow process. Okay, so once the tertiary carboxylic ion is formed, Br minus here will also be present here. Okay, So now when we produce our tertiary carboxylic ion, we're going to attack that with our weak nucleophile. So weak nucleophile, as mentioned, is water. So we're going to draw the water. So the water will attack using its lone pair, and therefore it is a fast process, and we're going to produce it to be something like this. So oxygen here will have a positive charge, and then we need to break the bond in order to make a lone pair here. Okay, so we're going to use the water, which is the weak nucleophile also, which will be used in order to attack one of the hydrogen, and then we're going to break the bond in order to pass another 2 electrons to the oxygen. And lastly, we're going to produce our tertiary alcohol to be here, which is equivalent with our structure of OH here. So it is equal to E. Okay, E here. And we started off with a D. So D can be converted into E by using this mechanism. So this is how we do question number 6. Now we're going to do question number 7. So for question number 7, the structural formula of compound H is shown below. So here is the compound H. And for the question number 8, we need to name the functional group of compound H. So from this compound, we know that this is the functional group. And the name of this functional group is the hydroxyl group. Okay, you cannot write it as alcohol because alcohol is the class of compound. So be very careful of that. So the functional group is supposed to be the hydroxyl group. Okay, and for question 7b, you need to suggest a synthetic pathway to prepare H via Grignard reagent and propanol. So Grignard reagent, Gr, and propanol here will have 3 carbon, 1, 2, and 3. And then it's going to have the aldehyde group, double bond O, and then H here. So it's going to have 3 carbon. So we need to make a Grignard reagent in order to link this one and this one in order to produce this compound H. So logically speaking, 1, 2, 3 here will come from the propanol part. Okay, so 1, 2, 3 carbon comes from the propanol. And the balance, 1, 2, 3, 4 carbon will be used in order to make the Grignard reagent. Okay, so the Grignard reagent comes from haloalkane, and then we can make it into a Grignard reagent, and then the Grignard reagent can react with propanol in order to produce the alcohol, which is the compound H. Okay, so that's the idea. So our haloalkane here will have 4 carbon, so it's going to be 1, 2, 3, and 4. And then we're going to pick one of the halogen, let's say Br. So 1, 2, 3, 4. So it's going to be bromobutane. Okay, and then this bromobutane here will be used in order to make Grignard reagent. So we're going to react that with magnesium as well as the triether in order to produce Grignard reagent. Okay, so it's going to be MgBr here. And from this MgBr here, which having 4 carbon, 1, 2, 3, 4, we're going to react that with a propanol, which have 1, 2, 3 carbon, and this will be followed by the hydrolysis, which is H2OH plus, in order to make 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. Okay, so total they have 7. So it is a combination of 4 carbon and 3 carbon. So the delta negative here will attack this side, and this one will make an alcohol. And as a result, we're going to produce 1, 2, 3, 4, 5, 6, 7. And then here going to be OH here. Okay. So this representing compound H. Okay. And for the marking, for this question B here, it will be consist of 4 marks. So identifying the haloalkane going to be 1 mark. Reagent, magnesium, and dry ether gonna be 1 mark, and then the production of Grignard reagent 1 mark, and then the process of hydrolysis followed by the propanol here will be another 1 mark. Okay, and here is 1 mark. So the other 2 marks come from question number C here. Okay, so let us read that. So for compound H, reacts with J to form K, which is C10H20O2 in the presence of a few drops of sulfuric acid. So we need to draw the structural formula of J and state the function of the sulfuric acid. So compound H will react with J in order to form K, which have a formula of C10H20O2 in the presence of sulfuric acid, which is few drops. So we need to draw the structural formula of J. Okay, so as what you know that our K here will have 10 carbon, but our H here we only have 7 carbon. So logically, our J here needs to be having 3 carbon. Okay, and here we'll have 1 oxygen, and then here we'll have 2 oxygen. So in this molecule here, it need to have 1 oxygen. Okay, so here is an alcohol, and here gonna be carboxylic acid, because alcohol reacting with carboxylic acid will help to produce an ester. Okay, so 3 carbon chain, which is carboxylic acid. The most simple one gonna be 1, 2, 3, and then double bond O, OH here. So it's gonna be propanoic acid. So you can written it in terms of the skeleton structure, or you can also put it in terms of the condensed structure here. Okay, so the structure that you will be getting is the propanoic acid, or you can also write it down as CH3CH2COOH. So here representing another 1 mark for identifying the structure. Alright, so let me clean that out. Okay, and for the sake of learning, we can also try to identify the ester, because you know that alcohol, when reacting with carboxylic acid, the OH here will be removed, and then H here will be removed in order to eliminate water. So the oxygen will be attached directly on this side here. So what we're gonna get is this structure, and then 1 and 2 here, I'm gonna put it down, and then single bond oxygen, and then I'm gonna link that with this structure in order to produce this kind of ester. Okay, so this one is just additional information. So we're gonna get the structure to be something like this. Okay, and then for the last part here, they ask us to state the function of the sulfuric acid. So the function of the sulfuric acid is to act as a catalyst. Okay, so this one will contribute to another mark. 1, 2, 3, 4, 5, 6, and 7. So 7 marks all together. So that's all for question number 7. Now we're going to do question number 8. So for question number 8a, we have to arrange the following compound in ascending order of the boiling point, and then we have to explain the answer. So we have compound L, which is CH3, CH2, CH2, COH, where we have 4 carbon, and then we have COH at the end. And then for compound M, we have CH3, CH2, CH2, COOH. So similarly, we also have 4 carbon. And for compound N, we're going to have CH3, CH2, CH2, CH2OH. So we have 4 carbon. Okay, and in order for us to determine it correctly, it is important for you to try to expand and to identify the functional group that is present in L, M, and N. So for L, if I were to expand the structure, what I'm going to get is 1, 2, 3, 4, and then I'm going to get double bond O, and then H here. So what I'm going to get here is an aldehyde. For compound M, I'm going to get 1, 2, 3, 4, and then I'm going to get double bond O, OH H, okay, which is a carboxylic acid. Meanwhile, for N, if I were to expand the structure, I'm going to get 1, 2, 3, 4, and then I'm going to end it up with OH here. So, compound N here is an alcohol. Okay, so from here, I know that my carboxylic acid will have the highest boiling point, followed by my alcohol, and lastly, the least boiling point, the lowest boiling point going to be my aldehyde. Okay, so this is because my carboxylic acid can form dimers, and number 2 here, which is my N, alcohol can form hydrogen bonding. Meanwhile, here will only have dipole-dipole forces. It cannot form hydrogen bonding. Okay, and from here, we're going to do the ascending order first, where the ascending order, it started off with uh, from lowest going to the highest boiling point. So the lowest boiling point going to be my structure L, followed by N, and then M. And then I'm going to make an arrow, which shows that there is an ascending order of boiling point. So this arrangement here will carry 1 mark, and then we need to give the reason. So for the reason is, we can say that for the M, which is the carboxylic acid, will has the highest boiling point in comparison to N and L, because M can form hydrogen bonded dimers. So from one carboxylic acid molecule to another carboxylic acid molecule, a dimers can be formed. So it can form more hydrogen bonding per molecule in comparison to N and L. Okay, and as for N will have a higher boiling point than L because N here is an alcohol. So alcohol can form hydrogen bonding. Meanwhile, aldehyde cannot form hydrogen bonding. What they can form is only dipole-dipole forces because it is a polar molecule. And therefore, we can say that the hydrogen bonding in N is stronger than the dipole-dipole forces in L. Hence, more energy is needed to break the intermolecular forces in N, thus resulting N to be having a higher boiling point than L. Okay, so this is how you answer question 8A. So in terms of marking, the arrangement here will have 1 marks. This hydrogen bonded dimer and the comparison will have 1 mark. And these two things together will carry another mark here. Okay, so they're going to be 3 marks for 8A. And then for question 8B, based on the following reaction scheme, we need to draw the structural formulae of P and T and give reagent Q, R, and S. Okay, so our molecule here, which is at the center here, is basically representing an aldehyde. 1, 2, 3, and 4. And then we're going to have double bond O and then H. Okay, so if you were to put it in terms of condensed structure, you're going to get the structure to be CH3, CO, CH2, C double bond O, and H. Okay, so this structure here can be formed from P, where P will undergo ozonolysis followed by zinc and H2O hydrolysis. Okay, so ozonolysis followed by the zinc and H2O, which is the hydrolysis process. So what's going to happen here is that P here is an alkene. So it will undergo oxidative cleavage in order to produce an alkene. So this alkene here need to be symmetry. Maksud symmetry, sebelah kiri dan sama sebelah kanan sama bilangan karbon dia in order to produce one type of compound. So the alkene need to be symmetry. So here you have 1, 2, 3, 4. You have 4 carbon. So logically your alkene gonna have 8 carbon. Okay, so let us draw that. So as mentioned, the alkene need to be symmetry. So it's gonna be CH3, CH2, CH2, C, double bond C. So we have 1, 2, 3, 4, 4 carbon on this side, and then we're going to have another 4 carbon on the other side. So we're going to have CH2, CH2, and CH3. And then here will be H, and then here going to be H. Okay, so when it undergo ozonolysis, okay, so this left hand side here for carbon will produce this product, and then the right hand side here will also produce this product by undergoing process of ozonolysis. And therefore, we know that this alkene here will be the answer. Okay, so our P here going to be an alkene, which is having we're going to have 8 carbon, 1, 2, 3, 4, 5, 6, 7, 8, and then the carbon-carbon double bond going to be symmetry on the left hand side and on the right hand side. Okay, and for the structural formula of T, which is here, we're going to react our aldehyde with the NH2OH. Okay, so the reaction between aldehyde with ammonia derivative will produces imine. Okay, in where they're going to eliminate water. So what they're going to do is that H2, let's say if I were to expand this structure, H, H, OH with a double bond here. So O and H here going to be removed. Okay, so HO will be removed in order to produce H2O, and as a result, my imine CH3, CH2, CH2, C, the place of the double bond here will be taken place by nitrogen, and then I'm gonna put OH here. Okay, so this is gonna be my last product, which is my imine. So my structure of T gonna be CH3, CH2, CH2, CH, double bond N, OH, which is this structure here referring to the imine. Okay. Now we're gonna look at into the next reaction, which is we need to give the reagent Q. So here is your structure, which is an aldehyde, and then you're gonna produce an alcohol. Aldehyde going to the alcohol. So the number of carbon 1, 2, 3, 4, 1, 2, 3, 4 is still maintained. So aldehyde going to alcohol is the process of reduction. Okay, so therefore for the reduction you can give reducing agent. Let's say my reducing agent is lithium aluminium hydride followed by H2O and H+. You can also use NaBeHa in methanol or H2 in platinum, palladium, or nickel. Okay, so this is one of the reducing agent that you can use. Now for the reagent R is here. So from aldehyde, you're gonna forming a carboxylic acid. So the number of carbon, which is 1, 2, 3, 4, is still maintained. It's just changing from aldehyde into carboxylic acid. So you know that it will undergo the process of oxidation. So oxidation, you're going to use oxidizing agent, where the reagent R that you can use is the KMnO4 in acidic condition with heat. Okay, so you need to write all of these things together in order to get 1 mark. Okay, meanwhile for the reagent S, you can see that 1, 2, 3, 4, it's going to become 1, 2, 3, 4, 5 carbon, and then it's going to have the alcohol. Okay, so from here, you know that you need to use the reagent S, which is Grignard reagent, because you want to increase the carbon chain. So you can use Grignard reagent with 1 carbon. So from 4 carbon become 5 carbon, which is CH3MgBr. And then in order to make an alcohol, you need to followed by hydrolysis, which is H2O H+. Okay, so for section B here, it will provide you with another 5 marks. So the determination of P, 1 mark, determination of T, 1 mark, complete reagent, 1 mark, complete reagent R, 1 mark, and complete reagent S, another 1 mark. Okay, so 5 marks for question B and 3 marks for question A. Alright, so that's all for question number 8. Now we're going to look into question number 9. So for question 9a, the treatment of the 2-phenyl ethanoic acid with alcohol U give an ester V with the molecular formula of C11 H14O2. Alcohol U will react with alkaline iodine solution to form a yellow precipitate W, whereas oxidation of U yields X. So for question 9a1, we need to draw the structures for U, V, and X. Okay, and as usual, if you were to read this information or these sentences just like that, it's quite difficult for you to visualize. So what I will suggest you to do is to make an idea or the reaction scheme. So let us start with an idea first. So it was stated here that we're going to have the 2-phenyl ethanoic acid. So 2-phenyl ethanoic acid will have 2 carbon ethanoic acid. So you're going to become 1 and 2. And then at carbon number 1, it's going to have double bond O, OH. And then at carbon number 2, it's going to be attached with a phenyl group. So phenyl group is basically a benzene ring acting as a substituent. Okay, so this is known as the 2-phenyl ethanoic acid. Okay, so you're going to be looking something like this. And then the reaction of this acid with alcohol U, which is U, will give an ester V. Okay, and this ester V will have the molecular formula of C11 H14O2. And it also stated that alcohol U react with alkaline iodine solution. So alkaline iodine solution, which is I2 in the NaOH. Okay, and this is going to give a yellow precipitate W. And then the oxidation of U will yield product X. So oxidation here, we're going to use an oxidizing agent. For example, the KMnO4 H plus with heat in order to produce product X. So we need to determine the structure of U, V, and X. Okay, so the information that you know from V is it have 11 carbon and it is an ester. And here is a carboxylic acid. So 11 carbon, and then our carboxylic acid will have 1, 2, 3, 4, 5, 6, 7, 8. It's going to have 8 carbon. So logically, our alcohol will need to have 3 carbon. Okay, so our alcohol can be 1, 2, 3 with OH, or it can be 1, 2 OH here. So it can be a primary alcohol or secondary alcohol. So which of these is correct? This one or this one? And in order to determine that, let us look into another information. Let's say U converted to W by using I2 NaOH. So from here, alcohol U react with alkaline iodine solution will give a positive result towards the iodoform test. So here is the iodoform test. So when it gives positive result, it means that this structure of alcohol will have methyl carbonyl group. So methyl carbonyl group must have the structure of C, CH3, OH, and H like this in order to give a yellow precipitate. And for this reason, the answer gonna be this alcohol here. So our U need to be a secondary alcohol, which is 2-propanol. Okay, and this one is not accepted because if this one is being accepted, it's gonna give a negative result. So that is why secondary alcohol is accepted here and not primary. And for the structure of V, when carboxylic acid react with an alcohol, a molecule of water gonna be eliminated. So OH gonna be removed here, as well as the H here. So O will be linked to here. So it's going to be producing this kind of structure. So 1 and 2. And then we're going to link with our oxygen. And then a single bond. And then divide it into 2 here. So here going to be the structure of our ester. Where if you were to count, you're going to get C11, H14, and 2 oxygen here. Okay. And since we know that our alcohol here is 2-propanol, when it undergo oxidation with a strong oxidizing agent, what we're going to get is a ketone. Okay, so now we have identified U, we have identified V, and then we have identified X from the reaction scheme that we have did. So we're going to draw it nicely here. So the structure of U going to be 2-propanol. For V, it's going to become an ester to be looking something like this. And then for X, the alcohol will undergo oxidation to form a ketone, which is the propanol. All right. And for question A2, we need to write all the chemical equation involved from the reaction scheme that we have did earlier. So we're going to start with the reaction number 1, which is on the right hand side here. So 2-phenyl ethanoic acid will react with U in the presence of concentrated H2SO4 with heat in order to produce an ester. So you need to write down all of this component correctly in order to get 1 mark. Okay. And then the next equation is the reaction of alcohol, which is your U, and then it's going to react with the alkaline iodine, which is plus I2, and you're going to make an arrow in alkaline condition in order to form carboxylic ion. So it's going to become C double bond O, O minus, and then Na plus will be closer to the negative charge, and this is going to form the CHI3, which is a yellow precipitate here. Okay, which shows the formation of iodoform or the triiodomethane. And then for X, for the formation of X is basically your U again, which is your 2-propanol. When it is oxidized, which is plus KMnO4, at acidic condition with heat, it's gonna produces a ketone, which is the propanol. Okay, so you need to do the equation 1 by 1, and the reagent must be added, and then the condition with the heating must be below the arrow. Okay, and then for question A3, you need to give the IUPAC name of W. So the IUPAC name of W is the 3-iodomethane. So if you were to expand the structure, you're going to have like this. Okay, so it is a methane because it have 1 carbon, and then it's going to have 3 iodine. So it's going to be tri because it got 3, and then we're going to got iodo, and then methane because it's referring to the alkane of methane. So it's going to be triiodomethane. Okay. Now for question B, we need to explain why the methanoic acid will give a positive result towards tolerance reagent, but ethanoic acid does not. Write the equation for this reaction. So methanoic acid is basically containing 1 carbon. Meanwhile, ethanoic acid will have 2 carbon. So methanoic acid, if you were to draw, you're going to get like this, and then H here. So here is the methanoic acid. For ethanoic acid, 1 carbon. For ethanoic acid, you're going to have 2 carbon, like this, and then it's going to end up with CH3 here. So this one is ethanoic acid with 2 carbon. So the methanoic acid will give positive result towards tolerance reagent. So the tolerance reagent is used to detect aldehyde. So when there is an aldehyde, it's going to give a positive result. Okay, so as what you can see here, the methanoic acid is very special because it have the carboxyl group, and at the same time, it's going to have the aldehyde group. Okay, so if you were to look at here, you're going to have C double bond O, and then you're going to have H. So they're going to have the aldehyde group. Okay, so this aldehyde group can give positive result towards the tolerance reagent. Okay, so that is the specialty of the methanoic acid. Meanwhile, for the ethanoic acid, it cannot do that. Okay, so you can give the reasoning by saying that methanoic acid contains the aldehyde group as I highlighted here, and then therefore it has a reducing properties and it can be oxidized using tolerance reagent. So it's gonna give the positive result. And then we need to write the equation. So here is our methanoic acid, and then tolerance reagent is basically AgNH3 bracket 2 plus, which is the argentum ammonium solution in alkaline solution in order to give carbon dioxide, water, and argentum, which is being precipitated out. And this is going to give a silver mirror. Meanwhile, for the ethanoic acid, when it is reacted with the tolerance reagent, which is using the argentum ammonium solution in alkaline condition, there will be no observable changes. Okay, and this is how the methanoic acid will give a positive result towards the tolerance reagent, where we're going to write the equation as well as the observation. All right, so that's all for question number 9. Now we're going to do question number 10. So for question number 10, the reaction scheme below shows the formation of a dye DD from benzene. So here is a benzene reacting with reagent AA in order to produce nitrobenzene, and then it undergo reaction with zinc H plus in order to produce BB, use reagent CC in order to produce this structure here, and then reacting with C6H5OH in order to produce DD, which is the dye. So we need to give the reagent AA and CC as well as draw the structural formulae of BB and DD. So from here, you starting off with a benzene. So from benzene going to nitrobenzene, we need a certain reagent. Okay, so benzene going to nitrobenzene, we need a reagent where it will undergo the process of nitration. So as what you have learned in the chapter of benzene, benzene can be converted into nitrobenzene by using a certain reagent. So this reagent here, which is AA, we need to use the concentrated HNO3 nitric acid, and we also need to use the concentrated H2SO4, and this reaction must happen at a certain temperature, which is between 50 to 55 degrees Celsius. So for the condition of AA, we will need to state all of this in order to get 1 marks. Okay, so concentrated HNO3, concentrated H2SO4, as well as the temperature of 50 to 55 degrees Celsius. And then we need to determine CC, which is here. So before we can determine CC, we need to determine what is BB first. Okay, so from the nitrobenzene, zinc and H plus here, it will allow the nitrobenzene to undergo the process of reduction. So nitro, it will be converted into amino group. So benzene ring attached to amino group, which is NH2 here, will becoming an aniline. So your BB gonna be an aniline, and then this aniline here will be converted into N2Cl. So if you were to expand this structure, what you're gonna get is a benzene with N triple bond N plus, as well as you have the Cl minus attached to the carbon-carbon attached to the nitrogen triple bond nitrogen here. So here, this reaction can be produced from aniline by using a certain test. So this test is known as the nitrous acid test. So for the nitrous acid test, we need to combine two reagents in situ. So it involves the reaction between NaNO2 with HCl at a very low temperature, which is 0 to 5 degrees Celsius, in order to produce HONO or HNO2, which is the nitrous acid. So you cannot write HNO2, but you need to write NaNO2 HCl 0 to 5 degrees Celsius because it needs to be written separately, where this is going to react in situ in order to produce the nitrous acid. And therefore for BB, we're going to write the aniline. And then for CC, It is a nitrous acid test where we're going to write NaNO2 HCl at 0 to 5 degrees Celsius. Meanwhile, for DD, it basically a reaction of this structure here, which is structure N2Cl, and then C6H5OH is basically a phenol. Okay, so you're gonna having the structure to be like this. Okay, I'm gonna write OH here. So it's basically a structure of phenol. So here is the C6H5OH. So what's gonna happen here is that this structure here will react with the phenol in order to produce a dye. So it's going to attack at the para position of the phenol. 1, 2, 3, and 4. It's going to attack here. So ortho, meta, para. It's going to attack at the para position where Cl and H going to be removed together in order to produce HCl, and then N triple bond N will be attaching at this para position. So what you're going to get at the end is you're going to get to be something like this. So you're going to get N double bond N. Sorry, here is double bond. And then this is going to attach at this para position of the phenol. Going to be looking something like this. And then it's going to be OH here. Okay, so what you're going to get is a dye by using a coupling reaction. So we're going to draw the structure to be like this. And for A2, give the name of the reaction. So the name of the reaction in order to produce a dye is a coupling reaction. We need to couple the N2Cl with the phenol. Okay. Now we're going to do question 10b. So for question 10b, we need to name a chemical test in order to distinguish N-methylamphetamine from aniline. So N-methylamphetamine is the structure given here. So it is a secondary aliphatic amine. Okay, this N here is attached with one carbon with another carbon here. So it's a secondary aliphatic amine. And for aniline, just now you have drawn it to be NH2 here. So aniline can be differentiated with this structure by using a certain test. So the most easiest one is to use the same test as given here, which is the nitrous acid test. So when aniline react with the nitrous acid test, where you have identified the reagent just now, which is NaNO2, in the presence of HCl at low temperature, which is 0 to 5 degrees Celsius, what you're going to produce is the structure given here, which is N2Cl. Okay, and this will not produce any yellow oil, and a clear solution going to be formed because this one is soluble in water, especially at the lower degree Celsius. Okay, and it will not give off a nitrogen gas unless it is being heated. Okay, meanwhile for the N-methylamphetamine, when you uses the NaNO2 HCl at 0 to 5 degrees Celsius, what you're going to produce is that you're going to get a nitrosamine. Okay, so this part here, NH, will be bonded with N double bond O, and this is going to produce a yellow oil. Okay, so for observation, you're going to say that the yellow oil is being formed. So there's going to be one negative result, and then there's going to be one positive result. And this is how you differentiated them. And you also need to name the chemical test because it asks you to name the chemical test that you have chosen. Okay, so for this part, the naming going to be one part. The chemical reaction going to be both of these are correct, will be another mark for the chemical reaction. And then observation, one negative and one positive will be another mark. Okay, so there are going to be 3 marks here. And then for question 10a, if you were to look into the previous pages, we can see that here will consist of 1 mark in order to give all the reactant correctly. This one another mark, this one another mark, this one another mark, and this one is another mark. So 5 mark with 3 marks here. Okay, so you need to give the name of the test, the equation, as well as the correct observation. All right. Also, you can try using the Hinsberg test. You can also use that in order to get mark. But as usual, name the test, do the equation, and then write the observation. Or you can use the bromine test, bromine water test. Okay, so this chemical test can also be used in order to get the marks. Okay, as long as your equation and your observation is correct. Okay, so that's all for question number 10. Now we're going to do question 11. So for question 11, the amino acid has amphoteric properties. By using serine below as an example, explain what is meant by the amphoteric properties. So amphoteric properties means that the amino acid, which is the serine, can act as an acid as well as a base. So we can put that explanation here. And then we need to write the chemical equation to show the amphoteric properties. So we're going to draw our serine, and the serine can act as a base when reacting with an acid to form salt. So serine, it's gonna act as a base when reacting with an acid. So let's say our acid here is the hydrochloric acid, and then this structure here, which is the serine, at this part here, which is the amino, it's gonna react as a base, and this one gonna be an acid. So base reacting with an acid, what we're gonna get is the salt of NH3 plus with the Cl minus. So the amino group will take up the H plus, and then the Cl minus will come closer as the electrostatic force between them is strong. And then, in order to show the amphoteric properties, serine can also act as an acid when reacting with a base in order to form salt. So serine now will be acting as an acid. So this part here is the acidic part, and NaOH is a base. So what's going to happen here is that this part here going to become O minus, and then the Na plus will come closer, where H and OH here will be eliminated to form water. So it's going to become O minus Na plus, and then water going to be removed as the byproduct of OH as well as the hydrogen here. Okay, so this is how you show the amphoteric properties of the serine. Next part is question number 12. So for question number 12 is the structure of Kevlar is as shown below. So we need to write the structural formulae of its monomer. So Kevlar is a polymer, and now we need to find the monomers. Okay, so monomers we're going to have two, because one will reacting with another one in order to form the polymer. And as what you can see here, we have the amide bond. So amide bond is from the condensation polymerization. So it's gonna remove H with OH. Okay, so you know that it's gonna eliminate something from the monomers. So the most logical answer is, let's say on this part here, I'm gonna separate that. So we're gonna get benzene, and then I'm gonna have NH, and then H here, as well as on this part I'm gonna get N, H, and then H here. And then my another monomer is gonna be like this, which is benzene ring, and then I'm gonna get C double bond O OH, and then C double bond O OH. Okay, and from here I'm gonna remove H with OH. Okay, same goes to the last part here and the earlier part here. So when they remove HOH, they're going to remove and eliminate water. And this part will link together in order to form the polymer. So N, H, C double bond O, and then you're going to link them together. Okay, and similar goes to the earlier part. And then we're going to put an N here. So the most logical one is put H and then OH here. So we're going to have one for diamine benzene and one for benzene carboxylic acid. Okay, or you can also use acid chloride, where you can use C double bond O Cl as well as C double bond O Cl. So you can eliminate water, or you can eliminate small molecule H and Cl, which is HCl. So the monomers that we're gonna get is 1,4-diamine benzene, as I have drawn earlier here. And then another possible answers for the monomers is by making carboxylic acid on both sides, as shown here, or we can change our OH to be Cl, which is the acid chloride. Okay, so here are the possible answer for these monomers. So here is 1 mark, and then either one of these will carry another mark, 1 or here 1 mark. So it's going to be 2 mark altogether. Okay, so I think that's all for past year question for the year of 2018-2019. See you again some other time. Bye!